Can you hear me?
Yeah.
Yes, great. So good afternoon, and I appreciate for allowing me to speak you today in this workshop. I am very sorry that I'm not in person, but last Friday in the Netherlands, a new lockdown was introduced due to the COVID and due to some infection, including in my daughter's class. I decided not to come to Cologne today. So I would like to give you my presentation online, and I would like to give you some sketches of the work that we have performed in the NATO AVT-296 work. That was a project that just ended now in June 2021. So the presentation will follow like this. The first is I will give you a NATO goal of a glance. Then I will go to the area of simulation and objective and subjective fidelity, or predictive and perceptual fidelity. I will concentrate a bit on the Qualification Test Guide performance standard, or the QTG. I will move on motion queuing and some work that we reviewed on the simulation fidelity based on handling qualities engineering. And I will end with some conclusions. So first, the NATO AVT at a glance. So the NATO group was started the work in 2018 and ended in 2021 with a final workshop in June that could be attended online. And the group was directed by Dr. Tischler. This was our first meeting in Liverpool, and you see Dr. Tischler in this picture, and co-chaired by Professor White, which is probably with you in the room.
Exactly.
So the goal of our work was to assess the state of the art on the Rotorcraft simulation fidelity and model system identification methods from the perspective of the researchers, industry, academic, and simulator developers. We had around 30 people participating in this group, so it was a very intensive effort. Many industries, universities, and simulator developers. And there is one report. It is Rotorcraft Flight Simulation Model Fidelity Improvement and Assessment, which is available. And it is, I would say, I would advise to read more detail, as we had a lot of work on that simulation fidelity. The work that we have done was mainly related to the simulation identification, and there were mostly related to the frequency domain identification. We had 7 different methods, as you see them in this enumeration, and we had a flight test database of a different 8 helicopters. The Bell, the UH-60, Sikorsky, CH-47 were amongst them. And the first 2 methods, so the gain time delay corrections and the black box input, they were more non-physical methods, identification methods. The next methods, method 3, method 4, 5, and 6, they were physics-based models. And Liverpool, for example, Linghai discussed as well on this forced and moment increments based on stability derivatives. And finally, the method 7, which is the stitch simulation, was performed by DLR and as well Dr. Tischler. And we as well concentrated on the quantitative fidelity, so on the metrics of fidelity, and on the perceptual fidelity as related to the simulation model. would say, okay, why simulation fidelity? So we are modeling the Rotorcraft or the vehicle. And because of this, we develop simulation models for different purposes. So the first question that we have is what kind of level of fidelity we need. And of course, we need simulation fidelity in order to increase the confidence in our prediction, in order to inform the design process. But we also need it to extend the safety and flight envelope expansion. We need simulation fidelity in order to reduce the costs and the time saving. And of course, we need fidelity in order to have more effective and efficient pilot and crew mission training. So if you would think of a simulation of the real and the simulated world, of course, in the real world, the pilot is perceiving the outside through this visual, vestibular, tactile, and oral system. And this is given to the central nervous system and further on to our motor mechanism, which is then controlling the vehicle. So we have the visual feedback and the orientation feedback, and we have the adaptive mechanism. And in the real world, this process is a complex process and involves as well organization, understanding of the information, decision. So there are many tasks involved in this. When we go to the simulated world, we can say that according to the task that we are performing, the pilot is trying to simulate, to fly in a simulator a certain task. So the first thing is that in a simulator, we are performing according to a certain task. First thing that we can discuss is the subjective fidelity or the perceptual fidelity, which involves the visual cueing, the control loading, and the motion cueing. Then we can discuss on the objective fidelity or the predictive fidelity, which is the real-time simulation computer. And here we have different low fidelity criteria in order to estimate our flight model. And finally, we can discuss on the behavioral fidelity, which is an integrated effect between the subjective and the objective fidelity. I would like to underline that in the fixed wing world, the fidelity, there are more definitions of fidelity. And in the fixed wing world as well, we work as well with the so-called environmental fidelity and the equipment fidelity. The environmental are the cues due to flight, and the equipment, those are the cues due to the simulation hardware. And actually, you see here, actually, that must be a trade-off between the environmental cue fidelity and the equipment cue fidelity. So in a training simulator, of course, we have a high level of environmental cue fidelity and equipment cue fidelity. For the research simulators, and those are can be used, of course, for assessing the new designs, we can think of a high environmental cue fidelity and less equipment cue fidelity. The procedures trainer can be used for training pilots. So here we need lower environmental cues, but higher equipment cues. So the concept of fidelity has a multidimensional character, and it depends on the application that we are considering. The high fidelity may not be the necessary for the effective training. And the critical dimension here is whether or not the device supports the specific objectives. And the simulation fidelity is actually an umbrella of terms which contain many terms like validity, accuracy, error, granularity, resolution, precision, tolerance, verification, and quality. So this is Fidelity is quite a challenge to think of. In the fixed wing world as well, there was a working group on Fidelity implementation study group, and they realized actually that going from the reality to the model, one needs to have one step in between, and that the so-called referent. And they say that referent, it is an entity or a collection of entities and conditions together with their attributes and behavior, which are present in a given domain. It is said that actually trying to assess the fidelity straight related to the reality, it would be a too intricate solution. So this is why we need actually to go to this kind of referent term. And using the concept of referent, we can simplify the fidelity measurements and go through that to assess the reality. Going on the simulation motion perception, we had in the NATO group a special section dedicated to the motion perception. And why? Because motion is a kind of holy grail for simulation fidelity. So we all know that we assess the motion, we perceive the motion with our vestibular system, which is formed by the semicircular channels, which are sensing the angular acceleration, and the otoliths, which are detecting the translational acceleration. One should think that how do we perceive, how important is the motion? And it came this question in the group already. One should understand that actually from an experiment in Simona in the simulator in Delft, we understood that actually the motion perception, it has a lead as respected to the perception of the visual. So what you see here is the roll rate in an experiment, and this is the continuous line is the stimulus, the roll rate, and you see here the semicircular channel response and the visual channel response. So contrary to what we think, the first thing that pilots are doing, they are perceiving this motion and then the visual cues. And sometimes, for example, in this experiment, the lead was about 300 milliseconds. We also know that for reproducing the motion cues, we need sometimes to give false cues. And here is, for example, one example of Liverpool work where they were simulating the motion cueing for the roll motion. And in order to reproduce the roll motion, the correct cueing of roll motion, they needed to introduce a false cue in a sweep. So going to understand the motion tuning criteria, mostly we have criteria as concern the motion. The most known are the so-called SINACORI criteria, and they were developed in 1977 and they were extended in 1999 by Schroeder. SINACORI realized that we can assess the motion of the perception of the motion by analyzing the motion at 1 radians per second. And he developed a rotational rotational gain and translational gain as a function of the phase error, and 3 different fidelities. High fidelity, where the motion sensations are close to those of visual flight. A medium fidelity, the motion sensations are differences and noticeable, but not objective. And the low fidelity, which is differences are noticeable and objectional. It was also understood that these criteria are actually have little or no support other than intuition. So they are quite subjective, but up to present, these criteria are the most used in the research. In the fixed wing world, there were the so-called developed the objective motion queuing testing, the OMCT, and the OMCT was introduced in order to eliminate this subjective character of a motion tuning. The OMCT is actually exciting each degree of freedom in frequencies between 0.1 up to 16 radians per second. And for example, you see an experiment in Simona where the OMCT is assessed for a surge motion. And the different frequency response of each degree of freedom is determined. And also in the test, the important relation between the input and the output response of the motion is determined. The OMCT are introduced in the fixed wing world in the ICAO 9625 element documents, and they are used in the present for the motion tuning. Going to the simulation qualification. Of course, we know that the FAA and the EASA, they have the so-called the objective qualification and the subjective qualification. And the objective qualification, there are the area where the so-called performance tests are made, handling qualities tests and trajectory tests. Those are all qualification test guide. And the implicit assumption of these standards is that a strong quantitative match of the simulator components with the vehicle will ensure a high degree of simulator fidelity. Efforts in EASA are made to change this assumption, and this is, for example, the ICAO 9625, which acknowledges that if all these are fulfilled, this still does not guarantee fidelity. So in the previous work that we have done on the fidelity questions, we try to understand how good are the physical models and how much tuning is acceptable. What is the sensitivity of this fidelity to the modeling errors? What is the relationship between the fidelity, tolerances, and handling qualities? And what is the sensitivity of the pilot control strategy to this fidelity? The QTG, as we exemplified in the NATO report, so these are the static tests, the dynamic tests, and the trajectory tests, with all these tolerances which are included in the qualification testing. And we have applied for a different database. I would like to give you an example actually that can be useful for this group, and it goes actually back to a Gartner group that we have performed on the simulation fidelity. So those QTG actually involve a physical tuning, which is the model is changed based on the physical reasoning and can achieve 80% of the fidelity, and afterwards a non-physical adjustment. So the control gearing, feedback elements. And we proved actually in the Gartner AG12 with Professor Padfield leading the group, that actually, although we can have the model in fulfilling the tolerances, the handling qualities will not lie in the fidelity standard. This is one example that we have done, for example, for the longitudinal input response. And what you see here is the pitch rate, so the on-axis and the off-axis responses, and you see that we try to vary actually derivatives belonging to this initial baseline model and try to see a new model which still fulfills these the tolerances. What we saw is actually that when we perform the bandwidth phase delay criterion the handling qualities, although the model was within the tolerances, the handling qualities were moving from the level 1 to level 2 handling qualities. So the conclusion was that the simulation could lie in a different handling qualities to the aircraft and still meet the fidelity standards. So further on, we tried, for example, this was the work of the Eurocopter, so the Dauphin, the response to lateral cyclic control input. It needed a trade-off between the roll attitude and the side slip matches. So you see, for example, the roll rate and the pitch rate, and the roll rate was within this the tolerances. So both they were matching the tolerances. However, if you look at some other parameters, this is the roll before the model tuning, and this is the side slip. So you see this, the initial model and the model before tuning, before the model tuning. The model after the physical tuning, it improved the roll. So the tuning after the physically based, it improved the model, it got it towards the tolerances, but the side slip was varying. Finally, after the model was totally tuned, so the model non-physical adjusted, the model was within the tolerances, but the side slip was not according to the wishes. So this shows how difficult it is actually, because if you are getting one parameter within the tolerances, it can be that another parameter is escape those tolerances. And the question is if we have all the good requirements in order to catch these variations. In Liverpool, the project of lifting standards showed that actually the best is to try to integrate predictive and perceived simulator fidelity assessment. So this is how they did. They developed a procedure in order to assess in parallel the perceived and the predictive fidelity. So going from the simulator requirements and according to the mission task element, one has to assess in both sides the perceived fidelity and the predictive fidelity. And if the predicted level, it has differences between in metrics for the flight and simulation, are these differences perceived and predicted acceptable? Then according to this, we go back in the loop. And only when we have both perceived and predicted, we can say that we have a simulator that is according to the scope that we are developing. Finally, I would like to give you some example of one work we have done recently in Delft in project NITROS, which is conducted by Professor Paranta. It's a Marie Curie project, and one PhD has performed autorotation training. So the question was, what are the effects of the helicopter dynamics on autorotation training, performing transfer of training experiments? So the goal was actually to see how should we train the best for learning autorotation. So there were actually two configurations given to the pilots. There was one hard configuration with a high pilot intervention. So the desired performance in autorotation was achieved quite hardly. The autorotative index was varied in order to have a difficult to fly configuration and an easy configuration where a low pilot intervention was needed. Then what we did, the pilots that trained first the hard configuration, so those are the group of hard helicopter training, transformed to an easy task. And then we put them back transfer to see the back transfer. We put them back to see the hard, how do they, how much they learn from the hard configuration. For the easy configuration, the first pilots that were trained with an easy configuration, afterwards they went to the to train the hard configuration, and then they were back transferred to learn the easy configuration. What we have seen is that for both groups, the positive transfer is observed actually going from the hard to the easy dynamics, and not the opposite. Going from the easy dynamics to an hard dynamics was actually give no transfer of training to the pilots. So in order to think of the future pilot training, we should have the methodology that give them exactly the configurations to be trained, and also how to train novices and advanced pilots. So I will finish with some conclusions. The concept of fidelity has a multidimensional character, and it depends on the application. Usually the concept relates to the degree to which the characteristics of the flight simulator are matching the real aircraft. The simulation certification standards still reveal shortcomings. And as an example, so although the simulation could lie in different handling qualities, the aircraft still meet the fidelity standards, and the certification standards should address both the predictive and the perceptual fidelity. So I think I'm finished at the moment, and I go to Slido for the questions.